Hello. In this video, I will solve an example on how to solve a two-dimensional ODE system. It is an example from section 3.5. And as you see, there are different examples here, but I'm gonna work on example 6. Maybe I can pick. Okay, I'm gonna work on example 6. I hope you like it. Okay, so for each of the systems, there are actually 7 systems here. For each of them, we need to find the general solution. We need to make a phase portrait, and we need to classify the solution, the equilibrium actually with respect to type and stability. First of all, I should say that for this part B, I just showed you guys how to make a phase portrait of the case where we have 2 distinct real eigenvalues, okay? But of course, as I mentioned in the previous video, there are other scenarios like complex eigenvalues and repeated real eigenvalues. In those cases, I didn't show you how to draw the phase portrait. And in some examples here, there are those cases, okay? So if you encounter such a case and if you cannot draw the phase portrait of it, don't worry about it. You will not see that in your test, okay? But you will see in your test how to make a phase portrait of the case where we have 2 distinct real solutions, real eigenvalues, okay? And number 6 is actually one of those cases. So in this case, we have 2 distinct eigenvalues. So, okay, anyway, let's do it. So part A, find the general solution. To find the general solution, what do you need to do? We should find the eigenvalues, right? And eigenvectors. And for the sake of time, you know, I think I already showed you how to find the eigenvalues and eigenvectors in the previous video. For the sake of time, just let me write down the eigenvalues, okay? Lambda 1 is equal to -3, and lambda 2 is equal to -1. And what are the corresponding eigenvectors? V1 is equal to -1, 1. V2 is equal to 1, 1. Okay? So these are eigenvectors. So what is the solution then? So I should say, yeah, x equals, the solution is actually equal to, remember the formula, C1, E1, sorry, C1, V1, C1, V1, e to the lambda 1t plus C2, V2, e to the lambda 2t. Okay, so C1 is just a constant, V1 is the first eigenvector, -1, 1, e to the -3t plus C2 times V2, 1, 1, e to the -t. Okay, this is the general solution, all right? Okay, part B, make a phase portrait. So we need to find we already got the straight line solutions, right? Those solutions are coming from the eigenvectors. But we should also find null lines. And of course, after that, we should find the arrows. And we should also find 2 sample solutions. Okay, let me show you how to do it. First of all, let's find the null lines. So for x1, null line, what do? We should set dx1 over dt is equal to 0, right? And to get, okay, how do we find dx1 over dt? It is the first row in our matrix, right? So this is our matrix. So from that row, what we get is x1. So maybe I should write this way: dx1 over dt equals, look at the first row, -2x1 plus x2 is equal to 0. Okay, this is our first null line. And second null line, this time I should set dx2 over dt is equal to 0. So dx2 over dt is equal to what? Look at the second row this time. x1 plus minus 2x2 is equal to 0. Okay, this is the second null line. Okay, we got the null line. So let's draw the picture of the solution. Let's find the phase portrait. Okay. Okay, they're not really straight, but I'm doing my best. Cool. Okay. Now, let's find first straight line solutions. What are the eigenvectors? Negative 1, comma 1. Negative 1, comma 1 is, okay, this x is x1 and this is x2, right? Negative 1, comma 1 is, okay, I normally use red for the null lines. Sorry, for the straight line solutions. This is negative 1, comma 1, right? So the first straight line solution is this guy. And since the corresponding eigenvalue is negative, right? The eigenvalue is negative 3. It is directing through the origin. Second straight line solution is 1, comma 1. So it is this point. So we got this line. And similarly, it is directing through, it is, so corresponding eigenvalue is negative, right? So it's, the arrow should be through the origin. And what are the null lines? Let's draw the null lines, and normally I tend to use green for null lines. So from the first null line, I get x2 is equal to 2x1, right? And this is a line that's passing through the origin. And x1 is, when x1 is 1, x2 is 2, right? So this guy. And similarly, it's passing this point, right? This is the first null line. Oh, I had to cross the origin. Okay. This is x1 null line. And x2 null line is x1 is equal to x2. And again, for x1 is equal to 2, x2 is equal to 1, x1 is equal to 2. Which is this point, right? And similarly this point. So this is the other null line. This is x2 null line. Now, okay, as you remember, null lines are dividing our plane into 4 regions. This is the first region, second region, third region, and the fourth region. And you should find the direction of the arrows. We should find the arrows actually on those regions. And to do so, we should look at this inequality, right? For the case, okay, from the first null line, whenever negative 2x1 plus x2 is bigger than 0, remember, arrows are pointing to the right. Okay. Okay, and okay, this is the null line, right? And this null line, x1 null line, is dividing the plane into 2 regions. Just pick an arbitrary point on the region. For example, let's pick this point. x1 is 1, x2 is 0. Plug it in that point, 1 and 0. So negative 2 times 1 plus 0, bigger than 0. Is this true? No, right? Which means on this part, it is negative, right? So on this part, actually on the right part, there are 2 regions, right? This region and that region. So here, arrows are to the left, okay? Here is also left. And on the on the left part here, it is twirling to the right and to the right again. Okay. Next, maybe I can erase here. What about the next null line? x1 minus 2x2. Is it bigger than 0 or not? Again, pick an arbitrary point. Where's the x2 null line? This is the x2 null line, right? Pick an arbitrary point on the left or right. Maybe I can pick this point, for example, 2, 0. 2 times negative 2 is 0. Is this true? 2 minus 2 times 0 is 0. Yeah, this is true, which means here on this part of the half plane, it is positive, so it is directing through upright. The direction is upward, and here it is downwards. Okay. And now on this region, so we got all the arrows right here. And what is next? So let me pick another color. Now I know that on the x1 null lines, arrows are arrows are vertical, right? So if you look at here, arrows are vertical and arrows are pointing downwards, right? So it's downward in here. And on this part of the null line, x1 null line, if you see here, arrows are pointing upwards, right? So these are the solutions. Similarly, on the x2 null line, arrows are horizontal because x2 is not changing, right? Only x1 is changing. And on this part of the arrow null line, if you look at the directions, it is pointing towards left, right? So it's pointing towards left. And here it's pointing towards right. Okay, cool. I got all the arrows. Let me make it bigger. Now we're gonna fill the rest, right? Remaining part. So if you look, so here, right, arrows are getting smaller and getting through the origin. This is the equilibrium, right? Whenever the two x1 and x2 null lines are intersecting, this is the equilibrium. So, and okay, for example, here again it's coming this way and through the origin, right? Here also coming this way. Of course, from here to there, it's again directing through the origin, right? And from here to there, how can I go from here to there? Okay. All right, so we got the phase portrait, and we should find also two sample solutions. And to do so, we just need to follow the arrows, okay? For example, let me pick another color for that. Let me pick this green. And I think I have to make it a little bit wider, maybe. Yeah, it's too wide or not. Okay, so let's find two sample solutions. These guys are coming here, right? And from there, how does it continue? Actually, if you look at all solutions, they're all towards the origin, right? So it's here. Okay. And from here, I got this right. So maybe this can be one solution, or you can take all these guys as a solution. So you just need to follow the arrows to get the solutions, okay? All right. And this is B part. Now what about the C part? Pen size. I hope this is the correct size. And let me pick my colors. And for this is too thin. This is tilting. Okay. So classified equilibria. So for the classification, remember, there are different possibilities, and it totally depends the eigenvalues. Since in our case, both eigenvalues are negative and real and distinct, this solution is asymptotically stable nodes. This is not nodes. Or we call it sink, right? And why do we call it sink? If you look at all solutions, the solutions are coming through the origin, right? So origin is just like behaving as sink. It's just taking all the solutions through itself. So its type is asymptotically stable sink. Okay. All right. This is end of this example, and these are the other examples as well. You can look at the other examples. Okay. All right, guys. I will see you in the next video.